This must be smaller than this.
And I didn't get
Okay. Apparently ours not as small business.
I understood 4. It makes sense, but like that's work. That's not.
All
right.
4, no.
Let me get the screen up here.
I'm higher.
My hand was up first.
I'm taller.
You're fine.
I'm the chair. Not in the chair. What? Why am I?
Well, you're always like on the table.
All right. Anybody have on 6-4? Anybody have any questions on what?
Number 2.
Number 4. I mean number 6. Sorry.
Anybody have any questions on number 1?
No.
Anybody have any questions on number 2?
Yes.
Okay.
So you just set them equal to each other.
Yes, because whatever is lost by one is gained by the other, right?
Sorry.
So they're going to be equal to one another, but opposite in sign. So this ends up being the specific heat of this item.
And you cancel out the negatives.
Yes. Yeah. One would have lost energy. One would have lost temperature, but it cancels out. So.
All right.
Got that one. Yeah, 4 was completely over my head. Me as well. Me as well.
So you set them equal.
Yes, because whatever's lost by one is gained by the other. Yep. The specific heat of the metal. Guys, it is just way too much in here. All right, any questions on number 3? Okay, number 4 then. Okay. You don't know the final temperature of these. They're going to be the same value though, because they both end up getting to thermal equilibrium. Okay. The specific heat is the same. It can be ignored. Okay. So you can ignore that. And you had 100 grams over here. You had 80 grams over here. T final. So distribute 80 through, distribute 100 through, and just do simple algebra.
And then you add like
Yeah.
Yeah, that's right.
temperature final.
Final temperature.
We understand, but I didn't get it before. No.
All right. Any questions on number 5?
4.
I just went through 4.
Oh, like, I thought you were going to 6.5.
I have a question. I have a question here from
On number what?
this is the next section.
Okay. Any questions on 5, 6, or 7?
6, please.
Okay. So 6, you had 4.2 degrees here, right? Okay. So I'm doubling the amount of mass here, right? From 5 to 10.
Oh yeah.
So that's where the 2 comes from.
Okay.
And then the mass went from 100 to 1,000. So that's where that comes from.
Because you doubled it.
Yeah. Well, no, because you increase it from 10 grams up to 1,000 grams.
Oh, times it. And you just do that.
Yeah. Austin, can you go shut that door? He's just, it's just too much for me to try to
And then you just,
listen
so you
to.
just set it up in the chart and then
Yeah, dimensional analysis. All right, anything else on that page?
I don't think so.
These keys are all online. You guys know that, right?
I know
Yeah.
I was confused.
Okay.
Okay, question number 4. Is that what we all have?
Yeah.
Okay.
I don't know.
So any questions on number 1 here? How about number 2?
No, I didn't. So I looked at the key and I was like, you did this one? I did not.
Megan, did you have questions about it, honey?
No, I just wanted to.
Okay, you're good then?
Yeah.
Okay. Any questions on number 2?
No.
All right, how about number 3 or 4?
Four.
Okay. So for number 4, you have to take this and you have to get it up to 0 degrees Celsius. So you're going to use your mass of the ice times the 10.5 degrees because you've got to get it up to 0 degrees Celsius. And then the specific heat of ice is this value. So that's where I got that from. Okay. So that gave me this. Then I'm going to use, I have to go through the heat of fusion. So when you go from the heat of fusion, that is going from a solid to a liquid. And where did I get this from? Where did that come from? Was that a previous problem? Yeah, right here. Okay. So they gave me the heat of fusion for water right here. I have 36 grams of ice. Okay. I need to get that into moles because this is in kilojoules per mole. So I'm converting the grams into moles in this step. Then I'm using that heat of fusion right here, get it into kilojoules per mole. But these were in joules. So therefore, I want to get this into joules so that I'm in like terms. Does that make sense? So when I add these together, they add right. And then here, I've got the same mass, but now my specific heat is different because I'm dealing with a liquid. And that liquid is going from 0 to 22.5. I add all of those joule amounts up. And then if you want to convert it into kilojoules, you can.
Wait, so what was the second step for? Because you went from solid to liquid.
Yeah, that's the melting.
Oh, because there's no, yeah. I get it.
There's no temperature change there.
So that's why you would just.
There is no temperature change.
Yeah, I know.
Okay. And you've got to go back up and grab this guy to make that work. But you still have to use the mass there.
Well, thank you.
All right. Any other questions on 4? Does that make sense now? Okay. What about 5? Any issues with 5?
I got that one and I was excited about it.
I know. They're little happy celebrations that you do
I get quite excited.
sometimes. All right. Moving on.
This doesn't look that bad. Okay.
So we're moving on to enthalpy of the reaction here. So we've got reactions that can gain or lose energy as a reaction takes place. You can represent that in different ways. And you guys have seen this at the end of some of your problems before. And I told you, just ignore that for now. Okay? We're going to not ignore it anymore. Okay? So this delta H means how much energy is given off or gained. So here, this is a positive value. That means that energy, that this is an endothermic reaction, and that energy is going to be gained in this. Okay? So for both reactions here, when we go through this, you can kind of think of this as when you input energy in, you can almost think of it as a reactant. And that's kind of what you're going to be doing when we get into the next unit, which is equilibrium, because this heat is going to change. If you add heat or take heat away, it'll change which direction the reaction will run. And so you've got to kind of start thinking of that in terms of heat as almost being a reactant here or a product. Okay. So if this value is positive, you kind of think of it as a reactant. It's getting added in. You have to add in heat to make this reaction run. And that heat is then getting stored in the bonds as energy in the bonds of the product that you're making. If this value is negative, then that 180 would be on the other side. Okay. You don't actually write this into the equation, but you can kind of think of it that way. So we've got both reactions indicate that the reaction is endothermic. Heat is absorbed in the reaction, and that is 1 mole of the reactant is forming 2 moles of product. So how much heat is required to react 2.4 moles? This is kilojoules per mole. So you use your dimensional analysis to be able to figure out how many kilojoules that would make. If you had 25 kilojoules of heat absorbed, then you could flip that around and be able to figure out how many moles of NO you were producing. Typically, these are always at a constant pressure, so you don't have to worry about pressure changes. Here are some laws that we talk about. So the energy of the system is equal to heat times the work. Heat of the system, or the change in heat of the system, is going to equal the change in energy of the system plus the change of pressure times volume. I believe some of them are on your sheet. I take that back. I don't know that you need to memorize them. They're just helpful sometimes to know. So.
Are we going to use them?
No, I don't think so. All right, so we want to know if we had 7.25 moles of this guy. Is my pen not working? No, it's plugged in. There we go. We had 7.25 moles of H2S. We're reacting that with 9.34 moles of O2. How much heat would be released? So what's the first thing we've got to do here?
Add them. Do the whole reaction of 7.25.
No, you have to turn them into kilojoules.
Nope.
Right.
You're wrong.
Find out which one's an exit.
Yes. Find out which one is your limiting reactant. Very good.
It's the
Está muy bien.
Wow, I'm impressed by
Let me do the math here.
Yeah, let us figure this out.
9.34
Isn't it
divided by
H2S?
3.
Yeah.
That's 3.1. 7.25 divided by 2. That's 3.6. So 3.1.
I don't know.
3.1 is obviously smaller. Oxygen it is.
Oxygen is your limiter.
So oxygen is your limiting reactant. Okay. If you take 9.3 and divide by 3, right? If you're doing this mental math, okay, that's going to be a 3. If you take 7.25 and divide by 2, that's going to be 3.5. So that means your oxygen is going to be your limiting reactant. Okay. Does that make sense? How I did the quick mental math there, where I didn't need an actual calculator for it. All right, now I'm going to need an actual calculator. So I'm going to take my 9.34 moles of oxygen then, okay? And I know that for every 3 moles of oxygen, I have 1 mole of reaction. And I know for every 1 mole of reaction, I'm giving off negative 1120 kilojoules of energy.
No, you are not.
What does 1 mole of reaction?
That's for every 1 mole of react. For every time that this happens, that's called a mole of reaction.
So within the mole of reaction, 2 moles of H2O form.
Yep. Yep.
So it's like a number.
Yep.
So it's 3 moles of O2 because that's when you do the.
It's right here.
Yeah. Oh, duh. Okay. I'm an idiot. I'm sorry, guys.
Okay. So the 3 moles of O2 come from the coefficient in the equation. So what did you get for your answer here?
3,000.
Negative 3,487.
And if we're trying to keep with our sig figs, it would be 90, and that would be kilojoules.
They're gonna take stuff off in the APs or.
Yes.
So on the exam, there is 1 problem that counts for sig figs, and you don't know what problem that is, so you want to try to use them throughout so that you get that sig fig point if possible.
And constants don't.
Constants do not apply. It's the measured amount. So here, this is a measured amount. This is a measured amount. This is just considered a constant.
So that's why you don't use. That's why you use because that's how much it started.
Yep, I had 3 sig figs here. I need to have 3 sig figs in my answer. What if I put a decimal here? That's 4 sig figs, isn't it?
Yeah.
Okay, so keep that in mind. All right. Here we've got a reaction. How many moles of water were also produced? So we formed this much energy. How many moles of water were produced in that process? So you're going to start out with your 92.1 kilojoules. We know that this is 48.1.6 kilojoules because we want our kilojoules to cancel. So we're going to put them on the opposite side. And that's every 1 mole of reaction. And for every 1 mole of reaction, no, 2 moles. Right here.
2 and
Yeah, I see the 2. I
Oh,
got it.
clearly you didn't.
All right.
God. This is outrageous. Put me in a smarter class.
Okay. So when we go through that then, you should end up with 0.0382, and that's going to be moles of water.
Would that be negative?
Yeah, you kind of have to ignore the negative there because you're trying to figure out how much water is produced. So it's not going to be a negative amount because you're actually going to be producing that amount. So yeah, I would just take the negative. I should have probably not put it on there.
So when you're dealing with energy, it can be negative, positive, negative.
Well, I guess you could do it this way, negative, and then those will cancel because this is how much was actually produced, given off. And then those negatives would cancel then. Yeah.
So is it 2 moles of H2O? Is 2 moles of moles of
Oh,
gas?
yep. Ksenia's right. This should be moles of H2O here. Oh, geez, Jacob. Okay, better.
Works for me.
I was reading the head, and it says essentially the standard enthalpy change. I was confused with standard enthalpy.
Where are you at, honey?
So it's the first UV question of the section. Calculate the standard enthalpy change.
Oh, it's just doing the same stuff.
It's just
So,
Just different words.
yeah, this is the enthalpy change here.
Okay, that's what it is.
So I think that's that's your enthalpy change, and calculate the standard enthalpy change when. So they're trying to get you to do what we did in this problem here.
Yeah, but you don't have to worry about finding the.
Yeah. Yeah.
I just want to make sure.
Okay, now this is bond enthalpies. Okay. The main thing that you've got to remember here is bonds broken minus bonds formed. Where do we break bonds in our chemical reaction? When I have a chemical reaction here, where am I breaking bonds?
In the reactants.
In the reactants. When am I forming bonds? In the products.
I get it.
Okay, so keep that in mind. That's the big key for this section.
Hurt by that.
My back is hurting.
I think
I am just, I'm aching. Like that's a little creepy.
I'll give her back
How would
massage.
I be a pervert?
Ellie.
No, but that's like your teacher. Like, we look at your best friend.
Yeah.
It's not.
That's just creepy.
Once Ellie graduates,
Lippy is gonna
her and
retire
Lippy,
as soon as I
her and
graduate.
Lippy are just gonna.
I
And then
wish.
We're gonna move together.
She's gonna go down to Florida. She's gonna go down to Florida with her. You're gonna go to Florida and hang out during the summer with Lippy.
Yeah, like Lily, except ours is gonna be planned, not accidental.
Yeah.
Right, Lippy.
It's just creepy.
You don't want no bathroom for me.
That's just weird. Okay, so let's keep going here. In chemical reaction, the bonds in the reactants must be broken and remade into products. Does that make sense? Breaking bonds always requires energy. Making bonds always releases energy. This requires energy. This releases energy. If more energy is required than released, then you have an endothermic reaction. If more energy is released than is required, then you have an exothermic reaction. You can estimate the potential energy change for a reaction by adding up the bond energies for breaking all the bonds in the reactants, then adding up the bond energies for making all the bonds in the products. Like I said, if you're requiring more energy than releasing, it's endothermic. If you're releasing more than required, it's exothermic. Make sense? This is a table of standard bond enthalpies. It's typically listed by your different substances. So like carbon-hydrogen bond has this much. A carbon-carbon bond, single bond, has this much. And I think in your packet, I gave you a more extensive table, maybe?
No, it's the same one.
Oh, is it just that one? No, I did. Here. No, this is something different. Hold on. No, that's different. That's different. Never mind. Yeah, it is just the table that's in there. Okay. All right. So this table is given. Notice that double bonds have more energy and triple bonds have more energy than that. So you have to be able to find those bonds in here. And you have to be able to draw what's happening with these in, what your different things look like. Okay, what's your different. All right, here, Ellie, this is for you.
Basketball is my best friend. I saw that in a baby.
Basketball is my best friend. Bonds broken basketball minus bonds formed.
Did you come up with that?
She did.
Just shake your head, yes.
Yes, she did. We're best friends, obviously she does. Come on.
Lippy, do you go to all Ellie's games?
She does. She live streams over her house.
Do you actually?
Yep, she does.
Just say yes.
Let me go with it.
Ellie was scared of me her freshman year. I know
I
she
was
was.
scared of looking my freshman year. Look at us now.
Besties.
I
I feel like that's how everyone's initial reaction is, like scared to do it, and then they come to the class and then just,
Yep.
like,
I feel like.
All right. So you have to draw the molecule so you can determine what bonds there are and how many of each type of bond there is. So keep that in mind. All right. So step one, we are going to draw our reactants and we're going to draw our products here. Draw the molecules. Yeah. So you've got carbon, carbon, carbon.
I forgot how to do it.
Carbon, carbon, carbon.
And then you've got your hydrogens around that.
Yep. Wait.
Yeah, it's one of those. So this is-
We get it.
Come on, man. We can keep up.
Okay.
I was confused, but I figured it out.
Well,
You just not an option in this class.
02. 00, double, double.
Double double.
What's the thing where you see if it's like the right one?
Lippy, I'm gonna be gone tomorrow.
What?
Matthew,
you said.
Connections that has.
Alright.
I didn't
You are not best friends with Miss Flipping Nuts, and she does not care.
Yeah.
Actually, we are buddies.
Maybe if it was Elle, maybe she'd care, but.
Maybe she would really be caring. She'd probably be crying like that.
I got a double dose of L today. So.
Why? Oh, advisory.
Yep. We had a really good time. Actually.
Can I switch to your advisory?
Yes, please.
Can you request? Miss Flipping Nuts?
What?
Can you request please? I hate my advisory. If you're
All right.
advisor-
So here we have how many CC bonds? 1, 2. So we're going to find 2 times, and we're going to look at our chart, and we're going to find our CC on there. So CC on there, and it's a single bond, so that's 348.
Do we have to know these?
348. They would give you a chart of them.
Nice.
You have to know this, like how to do this.
Yeah, but you don't know.
But you don't have to memorize these things, no.
We're multiplying the 2 times 348.
Yeah, because you've got 2 of them. You've got one right here, and you've got one right here.
Okay.
Okay? Now, how many of these do we have? 8. So 8 times, and we got to go back to our chart and find that one. So that's 413. That's right there. Well, I don't know that it won't be.
Is it on the internet?
Oh yeah, I'm sure it is somewhere. But and then we've got a double bond for our oxygen, and we've got one of those. So we got to go back and find that guy. O2 here it says is 495. I know. All right. So we're going to multiply these through, and we're going to add them together.
Well,
Well, she says. We're adding them all together?
Yep. You multiply across, and then you add them all together to get this amount. So make sure that you can do that, and you come up with the same amount there that I have. We're not done, by the way.
Minus by the others.
Yep, you've got to figure out the other side as well. So go ahead and see if you can figure out the other side.
okay.
Wait, you multiply them together or you add them?
You multiply.
You multiply across, and then you add those values together to get your total amount.
I was getting a 495.
Oh, whatever.
Not be rude to me.
I did it. 4.95.
Oh.
4.95. Yeah.
Yeah.
Yeah. You know what we forgot to do?
What?
What?
What's the first thing we should always do?
Balance.
No.
It's not balanced.
God.
It looks pretty balanced.
It's not. It isn't. It's just a little
There's
less.
3 carbons.
Oh.
Two pairs.
Bro.
Lippy, do you have to do more of these now?
Well, it just affects this one right here
No.
because we haven't done this side yet, right?
So there's 5 times
5, 3, 4.
5 times 4.
Yep. So 5 times 1 times 4. Yep. And then you should come out with the right amount.
What's the right amount? Because I don't want to do the calculator.
6,475.
That's what it was.
No.
Oh, she just had.
Yeah.
She was
Wait
wondering
a
why.
second. So we times it by 3 and 4, whatever.
So here we've got 2 times 3 times whatever these are, right? This is for my OC double bond there. $7.99. And then I've got for my OH bond, I have 4 times 2 times 463. Multiply those, add them together, and you should get 8498
Wow, Al.
kilojoules.
This is a.
Bonds broken minus bonds formed
Negative number.
equals 2023 kilojoules, but it is negative. That means that this is an exothermic reaction.
No, would that be delta G? Or what would it be?
Delta H. Yep. So delta H equals.
Gosh, we're doing so good.
Oh, what, Lippy? You forgot to balance. I'll get it right for 8th hour.
Yes, you will, Lippy.
You guys should see me 8th hour. I actually look pretty confident in there.
Are we? Is the first thing you get
I
in
was
just kind of like
thinking
the
you'd be
trial?
Oh yeah, yeah. It's always the. You're always my guinea pig hour.
You got 2.
Yeah.
We're the cool. I switched
Yeah.
to 8th hour next semester.
Goodbye.
You'll get the good Lippy then.
We're 4.
You'll get the polished Lippy.
4, 4, 4.
Daily switches.
Thank God. Thank God.
I can switch back, guys.
All right, one more before I release you to work on things.
I can switch back.
So we are going to draw this guy out. I got my carbon, hydrogen, chlorine. Yes, it's already balanced. And then I have my bromine. And that's going to yield my carbon, hydrogens, bromines, and then chlorine. All right, already balanced. See if you can come up with the right answer.
I don't really want to.
What did Jordan say yesterday that I was like, you know what? I agree with you right there.
He said this is stupid.
Yeah, he said he's like that stuff, and I was like, yeah. I was like, this is like the only
Look,
time.
I don't want to do on the calculator work, so I'm just gonna kind of like it now.
I just don't get why he
She doesn't care.
No, I don't understand why.
There's not enough room to draw all of these.
Random things, like goes on a tangent and get this one.
You know what I
Never
thought was funny? Is that when Mr. Bud
Not the
was
actual-
like, this should only take me like 20 seconds. And then it takes 10 minutes to explain it to us. I'm like, oh yeah.
Oh, yeah.
I'm like, you are there. I'm like, I comprehend that, Mr. Butler. What if he just walks in here? I'd tell it all to his face. No, you would
All right,
not.
this is a 50-50 shot. It's endo.
Did you do the math already?
No, I just assumed that's
No, then not. You never do the math.
I'm having a hard time just finding the letter.
CH. We'll do the math.
So tonight you have 6-6 and 6-7. They are due tomorrow.
I can do that for you, Lippy.
Lippy, when is this class on?
35.
37.
All right, so I'm just gonna get into that.
You do homework. Oh my God, you're like a nerd.
Stays in here.
That's you.
You should come
Oh
over.
my God, stop being rude.
I don't have homework any night in this class.
You should stay in here with Lippy.
I don't have homework in this class, and I have
I now am teaching a 5th hour in here
No!
for the rest of the year.
No!
It's because.
That's
Wait.
how she feels